I welcome you all in this 10th lecture, which is entitled Influence Line Diagrams, SSB with Train Loads. So we are going to deal with simply supported beams, which are being traversed by train load. So what's a train load? Train load is a loading which is having three or more point loads which are having fixed spacing between them. So in this case, we are having a train which is led by a 20 kilonewton load, followed by a 15 kilonewton load, followed by a 10 kilonewton load, and followed by 15 kilonewton load. So this is a train which was coming from behind somewhere left of A, and then it entered the girder at point A. And slowly it kept on coming inside, and this is the positioning right now. And after some time, the train will simply pass towards this side, okay, like this. The train will pass after some time like this, okay. So train is going towards the right side direction. So during the journey it was traveling over the beam. Our questions are as follows, okay. We have to find out maximum shear force maximum at C. Okay, this is a section at C, which is at 8 meters from left support. And what would be the critical loading positioning and critical load positioning? Okay, it means that I'm asking you that when this train passed through the entire bridge, during that entire time, tell me at section C, which is located at 8 meters from the left support, at that section C, what was the maximum value of shear force? And when that maximum value of shear force was reached, at that time, where was the train? Where was the train? So tell me the critical load positioning of the train and also the maximum shear force it caused at section C. Similarly, the second question is find out bending moment maximum. Calculate maximum bending moment at C and same critical load positioning. Okay. So we have the basic assumptions that the girder is prismatic and simply supported, the self-weight of the girder is neglected, loads move without impact, and material behavior is linear elastic. So those are the basic assumptions. And the spacings between the point loads is also given to you as 2, 1.5, and 2. Okay. So if we have to find out maximum shear force at section C, you will have to draw the shear force ILD and bending moment ILD. So let me draw the shear force and bending moment ILD. Okay, so this point value is minus 8 by 20. So how much is minus 8 by 20? You can calculate. So negative ordinate is equal to 8 divided by 20, which is 8 divided by 20. This is 0.4 minus 0.4 and this is plus 0.6. Okay. So now you have to calculate maximum shear force. So for maximum shear force, there will be two categories. One is the maximum negative shear force and maximum positive shear force, because shear force is having two sections, negative and positive. So for maximum negative shear force, I am going to place my train in such a way that I am covering the maximum possible ordinates on the negative side. So this will be 20, 15, 10 and 15. So now we can calculate the value of uh, maximum negative shear force. But for that, I will need the ordinate values. So I need this ordinate, I need this ordinate, I need this ordinate, and I need this ordinate, which I already know as 0.4. So how I can do that? I can calculate it. Let's say this is H1, this is H2, this is H3. So I can write that this is 2, this is 1.5, this is 2. So 2 and 2, 4, 4 and 1, 5, 5.5. So 8 minus 5.5 is equal to 2.5. This remaining distance is 2.5. So I can write for H1, I can write H1 by 2.5 equal to 0.4 by 8. So if I solve this, I will get 0.25 divided by 2. It is 0.125 meters H1. This is 0.125. If I calculate H2, it will be equal to by 4.5 equal to 0.4 by 8, and this will be equal to 0.45 divided by 2. It will be 2.225 meter. Similarly, H3 will be equal to H3 divided by this is 3 and 4. 3 and 4 into 7. No, 0.5, 4.56. So this is H3 by 6 equal to 0.4 by 8. If I calculate this, I will get 6 for the 4 to the 8. So this is 0.6 by 3 equal to 0.3 meters. So now I can find out my maximum negative shear force value. Now I can rub this. Maximum negative shear force at C negative will be 15 into 0.125 plus 10 into 0.225 plus 15 into 3 plus 20 into 0.4, and this entire thing will be negative. So if we solve this, we will get the answer. Into 0.125 plus 10 into 0.225 plus 15 into 0.3 plus 20 into 0.4. The answer is 7.825 minus 7.825 kilonewton. Now, another important thing which you have to keep in mind is that this 20 kilonewton load is actually this 20 kilonewton load is actually bigger than 15 kilonewton load. Had this been an opposite case, that means 15 kilonewton was on this side, right side, and 20 was on left side, then you will take your train load one step ahead, and in the following situation also you will have to calculate. That means you will shift your train in this fashion, that 15 is here, 10 is here, 15 is here, and 20 is here. And if 20 is here, you will have to multiply this 20 with this positive ordinate h5. Okay, so in that case 2 would have been 15 into h2 plus 10 into h3 plus 15 into 0.4. These all come with a negative sign, plus 20 into h5, and you should calculate this value. But in this case, I don't need to do this because I know that 20 is greater than 15. And when 20, the bigger value, is multiplied by a bigger negative ordinate, that is 0.4, then I will get a bigger negative value. On the other hand, the case 2 is having plus. Entire minus thing is getting subtracted by the plus 20 into h5. So this value is definitely going to be shorter. But if the case is that the first leading load, which is 20 in this case, it is smaller and the trailing loads are bigger, you will have to shift the loading one or two times and get the new shear force value. Maybe those value might be bigger than the value which you obtained by keeping the train load in this fashion. You may get a bigger value by keeping it in this fashion. It is very much possible, because if the trailing loads are bigger, then those bigger load will be multiplied by smaller ordinate, no problem. The total value may become bigger. Okay, so you will have to do that kind of calculation, but in the present case you don't need to do that because your first load itself is the bigger load. So now coming to the second part, where we have to find out maximum positive shear force. For maximum positive shear force, keep your loading here like this. This is 20, this is 15, this is 10, and this is 15. And this is 2, this is 1.5, this is 2. And calculate these ordinates. This one is 0.6, you know. So calculate these ordinates. This will be your H4, H5, and H6. This is 2, this is 1.5, this is 2, and the total is 12. 12 minus 5.5. 12 minus 5.5, it is 5, and 6.5. This is 6.5. Okay, so calculate the H4, H5, H6 values. So to do that, you can write H4 by 6.5 equal to 0.6 divided by 12. 6 to the 12. So 0.65 by 2. This is 2 3 is 6, 2 to the 4, 2 5 is 10. Similarly, H5 will be equal to 8.85 divided by 2. This will be 0.24 is 8, 2 to the 4, 2 5 is 10. And H6 will be equal to 8.5, 8.5, 9 and 10. 10 means 1 divided by 2, this is 0.5. Okay, so this is my 0.5 height. This height is 0.425. This is 0.325. Okay, so now you can do the calculation of the maximum positive shear force. Maximum positive shear force. So shear force positive equal to, so this is 20 into 0.325 plus 15 into 0.425 plus 10 into 0.5 plus 15 into zero point 0.6. You calculate this, you will get the answer. Maximum positive shear force. So this is 20 into 0.325 plus 15 into 0.425 plus 10 into zero point 0.5 plus 15 into zero point 0.6. This is 26.875. Okay, so this is how you can calculate maximum negative shear force and maximum positive shear force. Right? So now we will do the second part where we have to calculate the maximum possible bending moment at the section. Okay, so for that one, we will have to draw the bending moment ILD. Okay, so that we can do on the next page. That here is my beam. And this is my section C, which is located at 8 meters. So the ordinate value you can calculate AB by L, which is 8 into 12 divided by 20. 4 to the 8, 4 5 the 20, 24 by 5. This is 4.8. Okay, so now this is my train. This is my train, which is having 4 loads, and the values are 20, 15, 10, 15. 20, 15, 10, and 15. So where should I place my train to get the maximum possible value of bending moment? Okay, to do this, um, you have the option of basically keeping the train load in such a way that you get maximum possible value of bending moment. So for maximum possible bending moment, you can keep, you have to apply this technique. Okay, what is the technique? Basically, we want average load on both sides to be equal. Okay, so you have to understand this carefully. This is my A, this is my B, and this is my C. Okay, so this is so first of all, let us assume that the train was coming from left side and it barely entered the beam. When it barely entered the beam, So the condition was this, that 20 was on the first and 15 was here, 20 was here and 15 was the last one. And the train kept coming, and a time came when the 20 kilonewton load, the leading load, just crossed my section C. So if that is the case, I will make a table. The table will have three columns. One will be the trial load, which is a load which is just crossing the section C. And then I will have the average load on C, average load on AC, and average load on CB. So you want to do this calculation. So first of all, you are crossing the 20 kilonewton load. Then average load on the AC will be 15 plus 20 plus 15 divided by 8. And average load on CB will be 20 divided by 12. So what is this value? You can calculate. 15 and 15, 30. 30 and 20, 50. So 50 divided by 8. This is 6.25. And this is 20 divided by 12. It is 1.67. So you can see that average load on CB is smaller than average load on AC, which is understandable also because only one load has passed and entered into the territory of section CB. Now you will let one more load pass. The train is moving towards the right and the second trial load has also passed my section C. Then the average load on the section AC, this is my A if you forgot. So AC will be 15 plus 20 divided by 8, and here the average load on CB will be 15 plus 20 divided by 12. Let us calculate this value. This is 35 by 8. This is 35 divided by 8, which is 4.375. And this one is equal to 35 divided by 12. 35 divided by 12, so this is 2.91. So still I can see that average load on CB is lesser than average load on AC. Okay, so let one more load pass. So if 20 kilonewton load also passes, then I have on section AC, the average load is 15 divided by 8. And here the average load is 20 plus 15 plus 20 divided by 12. Okay, so 15 by 8 is how much? 15 divided by 8 is 1.875. And this is equal to 20 plus 15 plus 20, 55 divided by 12, 4.58. Okay, now we will stop here. We will stop here that this is the critical load. This is the critical load at which my sign is changing. So let me keep this load on the peak of the ILD. So that means I will fix the position of this 20 kilonewton load here. So if I fix this one, automatically the others get fixed. This becomes my 20, this becomes my 15, and this becomes my 15. This is the train. So for this condition, so this distances are 2, 1.5 and 2. So this is 2, this is 1.5 and this is 2. For this condition, calculate the bending moment. That will be the maximum value of the bending moment at section C. Okay, so you can do that. You can calculate this height. You can calculate this height. This height you already know, 4.8. This height also you can calculate. So calculate. Let's say this is my H1, this is my H2, and this is my H3. So you calculate your H1. So this is 2, this is 1.5. So this is going to be 12. This is 12, and this is 2 and 1.5. This is 3.5. The remaining distance is 12 minus 3.5. This is 8.5. This is okay, 8 and 9 and 10 and 12. Okay. So this is 2. So the remaining is 6. Okay. So you can calculate H1, H2 and H3 like this. That H1 by 8.5 equal to 4.8 divided by 12. Similarly, you can calculate H2 divided by 10.5 equal to 4.8 divided by 12. And similarly, you can calculate H3 as H3 divided by 6 equal to 4.8 divided by 8. Okay. For H3, I am considering left hand side triangles, and for H1 and H2, I considered right hand side triangles. So I can calculate the value of H1, H2 and H3. This is H1, this is H2, this is H3. Okay. So this is 8.5 into 4.8 divided by 12. This is 3.4. For H2, I have 10.5 multiplied by 4.8 divided by 12. This is 4.2. And for H3, I will have 6 into 4.8 divided by 8, which is 3.6. Okay. So now you can calculate the bending moment maximum value, BM max. BM max at C will be equal to 15 into H3 plus 20 into 4.8 plus 15 into H2 plus 20 into H1. If you calculate this, you will get 15 into H3 plus 20 into 4.8 plus 15 into 4.2 plus 20 into 3.4. The final answer would be, let us do the calculation. We will get 15 into 3.6 plus 20 into 4.8 plus 15 into 4.2 plus 20 into 3.4. My answer is 281 kilonewton meter. Kilonewton. This is how we are going to do the calculation of maximum bending moment. Okay, some visibility was not good, so I'm going to compress this entire portion so that you can see what is hidden behind my picture. Now you can have a look here. Okay, so this is how we are going to do the calculation of maximum bending moment. So always remember the technique. The technique is to find out the average load on both the sections, and first of all, the left hand side section, the average load will be larger, and then slowly as you move one after the other, point loads towards the right side of the section of interest, then the average load at left side at one point of time will become lesser than the average load at the right hand side. So just at that section where it changes the sign, like here, you can see this 6.25 is bigger than 1.67, and again 4.375 is bigger than 2.91, but then 1.875 becomes lesser than 4.5. So this is my critical section which I am going to place at the peak of my ILD, and rest the other three loads will get automatically fixed. So this is how you can calculate the maximum shear force at a given section. Thank you very much.